All right, good morning, everyone. For those of you who don't know me, my name is Craig Scott. I'm the Director of Preservation and Research here at the museum. The Royal Tyrrell Museum and its Cooperating Society would like to welcome you this morning to the latest installment of the 2025 Speaker Series. The Cooperating Society is a nonprofit charitable organization, and since 1993 has been supporting scientific, educational, exhibit, and local community initiatives. Through the management of the museum shop, donations, and memberships, the Society plays a key role in helping the museum achieve its mandate, including providing support for the Speaker Series. I am delighted to introduce this morning's speaker, Dr. Brian Davis. Brian earned his PhD in zoology from the University of Oklahoma in 2011, and since 2013 is an associate professor in anatomical sciences and neurobiology at the University of Louisville School of Medicine in Louisville, Kentucky. In addition to teaching gross anatomy to medical and dental students, Brian maintains a research program focusing on the craniodental anatomy and evolution of mammals from the age of dinosaurs. He has an active fieldwork program in the western interior of the United States, most recently in the Jurassic of Utah. And outside of work, he's busy with a pile of boys at home, but still manages to find time to make beer, probably a necessity given the pile of boys at home. And he tends bees and he bird watches. And I'm especially happy to note that Brian arrived here yesterday with only a 10% tariff imposed, so he's a real steal of a deal. So, and with that introduction, would you please join me in welcoming Dr. Brian Davis.
Thanks, Craig. I appreciate that. Okay, mic's on, everything's good? Everybody hear me okay? Wonderful. Okay, I've known Craig for a little over 20 years. We overlapped a little bit in a visit of mine to University of Alberta up in Edmonton, where I was studying material under his care as a doctoral student. We overlapped quite a bit in early mammals, Mesozoic mammals, mostly younger mammals, the stuff he still works on. I'm going to be going a little bit further back in time. And talk about some of the cool things that we can glean from some of our earliest ancestors. So I want to lead off with just a little bit of intro. Most of you have probably spent a lot of time in this building and are very familiar with what paleontology is. But in case my aunt from Norman, Oklahoma is out there watching still, paleontology is not that. I still get news clippings about arrowheads and pottery and things like that from relatives. Although with the latest news about dire wolves, maybe paleontology is becoming a little bit more like this, but it's still not recreating Jurassic Park. Paleontology, especially the kind of work that I like to do, involves working with crumbly little partial bits of skeletal material and trying to make some kind of a story out of them. So finding fossils and figuring out what they mean, what they tell us. This is a family tree of mammals, relationships between living groups, and how they fit with fossils is really important for understanding the history of life on the planet. And we often have to deal with data like this. Ultimately, the point is to recreate the ancient world. Ancient world was a vibrant, diverse place. It's easy to think about the charismatic megafauna like these guys, but during the age of dinosaurs, there was a lot else going on, a lot of small little things that made the ancient world just as rich as it is today. You can go out in the woods and chase deer and large animals, but the staggering amount of little things scurrying around is what really makes biology really interesting. So the other thing happening during the age of dinosaurs is geography is a massive variable. So the beginning, here we are on the Triassic, so the beginning of the age of dinosaurs. The Earth is pretty unfamiliar. For a little bit of context, that's about where Drumheller would be, tucked up there. Most of the continents aren't really identifiable. By the end of the age of dinosaurs, you start to see a map that looks a little bit more familiar. But the moving of these land masses creates lots of opportunity for dispersal and endemism and all sorts of drivers of evolution and diversity. So when we're interested in fossils, these are the sorts of things we think about first. Big, beautiful, complete skeletons full of awe and wonder. But it's not just big skeletons. A fossil is just evidence of past life. It can be a carbon impression of soft tissue, like a feather. Footprints. Footprints are great fossils. They tell us a lot of stuff. Fossils can tell us something about behavior. Okay, this is a fossil beaver burrow. They didn't know what the thing was until they found a little beaver skeleton tucked at the bottom of it. That tells us something about how these things behaved. And poo. This is always a winner with kids. Fossilized poo. We call them coprolites. So these all tell us something about extinct animals. The kind of data that I'm used to working with, this is a good chunk of a mammal skeleton, right? That is my thumb there for scale. So you can see an entire limb in articulation there. That's a tooth from a T-Rex, and you can barely see it on the head of the pen is a tooth from the kind of mammal that I'm used to working with. This is the scale that these things were at. So fossils can be very tiny, and they're almost always very fragmentary. So how do we find fossils, especially when they're really, really small? Where do you even start to look? This is a fairly typical landscape of the Morrison Formation, where I've spent a lot of time in eastern Utah. Under this rock, over at this hill, look under the bushes. Where do you start to look? Most of these things are found by crawling around, walking slowly, looking at the ground, looking for little bits of interesting rocks that don't seem to fit the pattern of all the rest of the noise in the background. So this particular spot, this little hill here, I noticed the GPS unit wasn't there beforehand. That would be an easy way to find fossils. But you crawl up the little drainage here, and this little stringer of funny-looking rocks right there turned out to be most of a skeleton of a little stenodontian, which is this funny kind of lizard-like creature that used to be very common during the Jurassic period. Nowadays, they're represented only by the tuatara, which is this funny. This is probably the thing that Godzilla started as. They're only native now to New Zealand. But you find little bits of bone weathering out of hills. That's how most small vertebrate sites are found. You can employ a bunch of students, and everybody gets butts in the air, and you crawl around with your nose right at the surface, and that's a great way to recover little bits of small vertebrates weathering out at the surface. So we have fish scales, fish teeth, there's little bits of crocodile teeth, and you can find tiny dinosaur teeth, little bits of vertebrae, mammal teeth. The thing these have in common is these tend to be the hard parts of a skeleton. So enamel survives fossilization really well. So most of our record of small animals is restricted to the hard parts that fossilize. Teeth fossilize really well. So we've got a pretty good record of small things based on these types of fossils. And if you find a horizon in the rock that these little things are weathering out of, one method to get a lot of bang for your buck is bulk sampling. So high-tech techniques using burlap sacks and shovels. You just collect this rock, and you collect as much of it as you can. You're rarely by the road, so these 80-pound bags of rock have to get humped by hand from wherever you're filling them to wherever you can stack them by a road. So this would represent a pretty good season's haul of rock, this big stack of bags. Getting them out from here is often an adventure. You can fill entire talks with field catastrophes, trucks getting stuck, all that sort of thing. But it's always an adventure. So what you do with those bags of concentrate, one good way of separating out the good stuff from all the sediment is by using nested screen boxes. So these are boxes that fit inside of each other with different size mesh. You can do this in the field. You can do this back at the museum. Set up these cattle tanks, and you let the rock soak, and that water gets in and busts up all the sediment. And then you shake out the sediment and let the resulting concentrate dry. Okay, and you can repeat this and process a lot of rock in the field and then bring it back home. What's really fun is when you're actually working the screen boxes in the tank, you never know what kind of stuff you might find. Sometimes fossils just appear in the boxes. Rarely this complete, but sometimes they are. And at the end of a season, you can end up with a really good sample of all sorts of little things. This is a great way to get the picture of all of the small vertebrates that might have been running around in a particular spot. you're not limited to that one beautiful skeleton of a dinosaur. You get pieces of lots of little animals. A whole tray of fish scales, chunks of turtle shell. You get vials with little teeth in them. Great student projects, volunteer projects, that sort of thing. So a lot of the bulk of small vertebrate sampling happens this way. So I'm going to turn to a locality that I've been working in a slightly different manner for the last almost 10 years. This is where I've spent my limited field time in the summer. This is a site that I ended up naming the Cisco Mammal Quarry after it turned out that mammals are relatively common there. This is in eastern Utah, not far from Arches National Park, so it's real pretty country. And this is in the Upper Jurassic Morrison Formation. We've got a pretty good radiometric date on it, so it's right at about 150 million years, so near the boundary between the Jurassic and Cretaceous periods. So this is how this locality was found. That little crumbly bone sticking out of the top of the hill in this weathered popcorn surface was all that hinted at there was a pretty good locality here. A little bit further down, a slightly better limb bone sticking out of the rock. And it turned out that this is on the large side for most of the fossils that I've found in this locality. Everything is really, really small. I still don't really understand why, but this locality, this unit, the Morrison, for those of you that aren't familiar, is the same rock unit that Dinosaur National Monument is found in. Charismatic, giant, famous big dinosaurs, Allosaurus and Diplodocus and Apatosaurus and those sorts of things. They're what this rock unit's known for. So to find a locality that only preserved small stuff was really exciting. So here's how this locality has worked. Clear off the surface of all the weathered bits, and the rock is really hard. We end up breaking things with sledgehammers, small hand sledges. So you roll out a kind of a basketball-sized boulder, and you look for little dark specks on it. Everything is really small. It's all done with hand lenses. If a particular specimen looks enticing, we very carefully wrap it up, again using high-tech field techniques, toilet paper and masking tape and a 5-gallon bucket, and then it goes back to the museum where it's processed. Most of my work still happens at the Oklahoma Museum at the University of Oklahoma, where I did my graduate work. So here's an example of some of the stuff that I've found in this. So this little dark smear on a background of gray rock is exactly the kind of thing that I'm really excited about finding. Doesn't look like much, but if you look closely, there's a row of little circles. Bing, 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 bing. Those circles are tooth roots in cross-section. So that tells me that this chunk of amorphous dark stuff has a bunch of teeth in it. For scale, that's how big this thing is. That's about typical. Very, very, very small animals. From here, we will mechanically prepare specimens when we have to, but these are very small and very delicate. So the magic of micro CT scanning has really unlocked a lot of what we can do with this locality. So you CT scan this piece of rock, and that's what that specimen actually looks like. Okay, this is a maxilla and a palate from a little early mammal. There's that row of teeth that you can see in section right there, and you're looking at the nasal cavity, that's the palate, and that's the side of the snout of this early little mammal, which is very exciting, very publishable. What's really, really fun about paleontology is the limitless possibility to find new stuff, things that are truly new. In biology, it's unmatched other than studying ants on rainforest islands, or maybe one day looking for life on other planets. But paleontology is really the best way to go out and find something truly novel. And you get to name it, which is really fun too. So I named this thing after my graduate advisor, Rich Cifelli. He's a guy that's made tremendous contributions to the study of early mammals, and you get to name it for where it's from. A little ghost town called Cisco, Utah, nearby where this locality sits. So that part's been really, really fun about early mammals. Another really cool thing that we found here is this guy. This is an animal called Fruitifossor. It's only known by one or two other specimens. And I've got a really nice skull, matching jaws, and a good chunk of the front of the skeleton. This is what the humerus looks like in this animal, the upper arm bone. So If you're familiar with your humerus, it's long and skinny and relatively uninteresting, but this humerus is short and fat and really broad, and it resembles the humerus on a mole. This is an animal that's heavily specialized for digging. It would have spent a lot of its time underground. And again, my fingertips for scale. So it's a very, very, very tiny animal. We've CT scanned this thing. This CT data from these localities work really, really well. We've got a second skull fragment. I'm going to come back to these things in a little bit later, and I'll talk about some of the stories that we can learn from them too. So what? These are funny early mammals. They may tell us a story about what mammals may have been doing during the Mesozoic. What does that have to do with mammals today? Which, the relevance of why we go out and break these rocks. Because it's fun doesn't usually work with grant agencies and administrators. So this is a family tree of roughly of what modern mammal diversity looks like. Okay? And trees can make your eyes go crossed. So it's always nice to have pictures of what these little twigs on the tree represent. The vast majority of mammals that are alive today are familiar. If you think about if you name a mammal at random, you're probably naming a placental mammal. So this is the group that we are included in as well. So they have a relatively familiar mode of reproduction, and they represent the vast majority of the diversity of modern mammals. Another much smaller group, kind of curious little critters, marsupials. A different mode of reproduction. Okay, they're born as a little jelly bean that has to then crawl up and finish development in a pouch, which is pretty neat. They represent a much smaller share of modern diversity, but that's not all. We have one more group called Monotremes, which I'll touch on in just a sec, and they are weird. So placentals, again, tremendous diversity. Everything from dogs to whales to bats. All sorts of cool things are placentals. Placentals have a long history. They likely appeared in the fossil record sometime around the end of the Mesozoic, when dinosaurs went extinct. Placentals back in the age of dinosaurs would have been pretty generic looking. Little mouse things, little jumpy things, climby things, but nothing really remarkable. Kind of generic little mammals. Marsupials are far less diverse today. There's not very many of them, and they're relatively conservative in their morphology. You get things that are cool like kangaroos, but most of the rest of them have kind of a possum sort of shape to them. Back in the Mesozoic, they were a little more interesting. This is one that probably behaved like a river otter, which is pretty cool. We don't have anything like that around today. But still, relatively generic, recognizable. Nothing too crazy happening during the age of dinosaurs with marsupials. Monotremes. Monotremes are crazy cool. They are very, very, very rare and not very diverse nowadays. There's the platypus and then a couple of species of a spiny anteater called an echidna. These are restricted to Australia and the surrounding islands. They're not found anywhere else. Their biology is super weird. Their skeletons are super weird. In a lot of ways, they are like a fossil group. They're very primitive in a lot of respects. They have this sprawling posture where their limbs stick out sideways, kind of like a lizard, which is really cool. The male platypus is venomous. It has this little combat spur on its heel, which turns out to be something that we see in the fossil record of mammals much more frequently than we do now. Other aspects of their skeleton and biology are pretty primitive. The coolest thing about monotremes is they lay eggs. So they lay this little kind of ping pong ball leathery egg that hatches after a short period, and a little jelly bean-like, kind of marsupial-like embryo crawls out. And monotremes don't have teats, but they still make milk because they are mammals. So the little baby, the hatchling, will crawl up onto a patch of skin on mom's belly and lap at a field that milk is produced in instead of on a teat. And they look like this too. They're really cute. I like putting this picture of these guys up there. They go by puggles, I believe is the term for baby monotremes. Aren't they sweet? But what are they? What's their story? How do they fit in with the rest of modern mammals? They're really primitive and weird in a lot of ways. I mentioned that teeth are a really important data source for what we know about ancient diversity in mammals. Living monotremes don't have any teeth. They're completely edentulous. So this is the skull of a platypus. Where it should have teeth, it has this little horny pad that it uses to squish up crayfish and whatnot. It has teeth kind of ephemerally during development when it's young, but then they fall out. So putting monotremes in a context, in a fossil record built from teeth is really difficult. And that's where paleontology can really come in. A fossil platypus was found. Looks all the world like a living platypus, except it's got teeth, which is really cool. 15 million years old. That's not really very old, though. But what that does do is it provides a dentition, kind of what the teeth looked like in a platypus. So then when you look further back in the record, there's a whole array of early mammals from the Cretaceous period of Australia that were really hard to fit into a context of modern animals. So a jaw with some teeth now can be compared to a platypus with teeth, also fossil. And now we know that this group of animals from Australia, way back in the Cretaceous, deep in the age of dinosaurs, actually represents a fossil monotreme lineage, probably fossil platypuses, which is really cool. So these fossils can help unlock, allow major breakthroughs in linking kind of weird-looking fossil and even living animals to the big picture of life on Earth. So ultimately, to understand how all these features we see in living mammals evolved, we really have to look at fossils. Fossils also tell us how ancient communities, ancient diversity responds to major events on Earth, whether it's changes in climate, extinction, recovery. But most importantly, fossils record combinations of features, of characters that aren't around anymore. So fossils provide a really important source of data. Whales with limbs, gophers with horns, tiny horses with 5 toes. These character combinations don't exist anymore. We only have access to them through fossils. And that's what's really cool about going out and collecting stuff. So if we try to look more broadly, comparing mammal anatomy with other living vertebrate groups, the next closest living group to mammals, you have to go all the way over to reptiles. There's no other living vertebrate group that's closer to mammals than the big group that we just consider broadly as reptiles. So if we go down to the closest common ancestor between mammals and reptiles, you have to go back more than 300 million years in the past to find what that common ancestor looked like between the mammal line and our closest relative, reptiles. And that's kind of what this animal would have looked like. Does that look like a mammal to anybody? I hope it doesn't. It doesn't look anything like a mammal. So going back this far in time to find a common ancestor, what does it really tell us about mammals? Anybody with kids, you can buy a bag of plastic dinosaurs, looks something like this. And they always include this guy. This guy's always in a bag of plastic dinosaurs. But it's not a dinosaur. That thing with the sail on its back is actually a stem mammal. So that is more closely related to you than it is to T-Rex. So this is a stem mammal, always in that bag of dinosaurs. This is a slightly closer relative to you as a mammal, but a fair question is, what do either of these things have to do with what we would see familiarly as a mammal today? They don't seem to resemble mammals very much at all. They look a lot more like a reptile. So we just have to look at our anatomy, look at the anatomy of mammals, things that make mammals special, and there are some really, really cool stories buried in there. And the lower jaw actually tells a really, really cool story. There's lots of directions you can go with this. We use our lower jaws. Lower jaws have teeth in them. We use our teeth to chew. You will not see any other vertebrate group alive today chewing their food. That is a mammal feature. Mammals have these complex teeth that fit together to crush up bugs and get all the calories they can out of them to drive our really high metabolic rate. So that's a whole different story That's all closely tied into what I'm going to take with this. Your lower jaw as a mammal is made of one bone. That doesn't sound remarkable, but if you look at the lower jaw in other vertebrate groups, they're compound. There's the bone that has the teeth in it, and then a bunch of other bones behind it, and then the bone that actually attaches to the skull. So the jaw joint and the back of the jaw itself is very different between mammals and other vertebrates. This is a lizard here. And if we look at an extinct animal that's closer to mammals than it is to reptiles, we see that the back of the jaw, as we'd expect, we're coming from a reptilian ancestry, a reptile-like ancestry. Our lower jaw, as early in the mammal line, looks much more like a reptile than a mammal. So we can turn to embryology. There's the old maxim that ontogeny recapitulates phylogeny. The way an animal develops tells something of a story about its evolutionary history, which has some truth to it. So this is a little animation from a really cool documentary several years ago that was on PBS called Your Inner Fish. And this is just going to show a series through the development in the lower jaw and the ear region in a living possum. They're great. You can study them and learn lots about development. And early on in development, here's the lower jaw and the ear, like how the jaw is attached to the skull. And it resembles a lizard in its construction a lot more than it does an actual a living mammal. So start this going. Pay attention to what's happening back here. So as the jaw grows, the bones that used to attach it to the skull shrink in comparison. And they eventually detach and drift off and become our middle ear bones. So the middle ear bones used to be the bones that held the jaw to the skull. So by the time development's over, then we see what the kind of living arrangement looks like. So it's a cool story through the development of a possum of what the lower jaw, how it transformed during the history of mammals. And another way to look at this, these are CT renderings where the homologous bones, the bones that are the same bones are color-coded. The bone with the teeth in it, the bone with the teeth in it. The bones attaching the back of the jaw to the skull, and the middle ear bones in a living mammal. What we just saw in development, the back of the jaw is attached via the ear bones to the skull early in development, and we see the same sort of pattern in a fossil relative, a compound back of the jaw attaching to the ear region. So your middle ear bones you're using to hear me right now are the same bones that held the jaw onto the skull in a Tyrannosaurus or a crocodile, which is a really cool story. And it's really only unlocked by looking at fossils. So we go from a compound lower jaw and this cool sail-backed reptile that's really on the mammal line, an animal called Dimetrodon. The lower jaw bones begin to reduce and slowly detach until they end up as free-floating middle ear bones in living mammals. And this is what your middle ear looks like. Same bones that used to hold the jaw onto the skull. So I'm going to switch gears and talk a little bit about how the ear works. This is a similar chunk of slides I would give to a medical student. They have to suffer through comparative anatomy and fossils, even though all they care about is learning about human anatomy. That's what they get by having a paleontologist as an anatomy professor. So here's where your middle ear bones live. They are very, very tiny, tiny, tiny bones. By far the smallest bones in the human body. Okay? And they transmit vibrations from the eardrum to this cool series of fluid-filled tubes in your inner ear. Okay, this is where the receptors are for hearing and also for balance and equilibrium. Okay? And this coiled set of tubes here is a structure called the cochlea, because it resembles like conch and cochlea have the same origin. It resembles kind of a snail shell. And it's a bunch of fluid-filled tubes that vibrations travel through and rattle membrane receptors. And the ear structure in mammals is really, really cool because this vibration that gets transferred to the fluid in your inner ear will set this membrane into vibration as well. And this membrane changes in stiffness along its length, and each portion of that membrane is tuned to a specific frequency, and it will vibrate in harmony with that frequency. So something like A440, I'm not a music person, but this seems to be a reasonable, you find a key on the keyboard that's a specific singular tone. There is one spot in your ear that will vibrate at that pitch. And as that specific spot vibrates, an impulse is sent through nerves to your brain where you encode that specific frequency and you can make sense of it. Oh, that's the sound of a hummingbird. That's the sound of a baby crying. That's the sound of a predator coming. And the mammal ear is really, really special because we have 3 independent ear bones and a long, highly coiled set of receptors in our cochlea. This is a bird. It's a fairly derived, complex version of an ear relative to other non-mammal groups. A single ear ossicle and a relatively short patch of receptors. We have 3 bones and a much longer patch of receptors. This is what your inner ear looks like. This is a human. Here's I think we have a frog, and we have a lizard, and we have a crocodile, and we have a bird. So very, very, very kind of unrefined receptors for hearing in other vertebrate groups. And I know that showing complex charts is difficult in seminar contexts, but what I want you to see here is everything in this box. Okay, this is the spectrum of hearing sensitivity from low frequency to high frequency. This box contains mammals, with one exception that you might not surprise you: owls. Owls hear pretty well relative to other non-mammal groups. But non-mammal groups are restricted to relatively low frequencies. So the high frequency realm is the realm of mammals. So only mammals hear really high frequency sounds. And that's likely a big driver of our success during the age of dinosaurs. Whether it's hearing nocturnal insects and taking advantage of that food source, whether it's communicating with our own species at high frequencies where our predators, who were all dinosaurs and other reptiles, couldn't hear us. Hearing is likely a really, really important driver of mammal evolution. And we can see that in these. And hearing is, not surprisingly, something that is easy to see as a major feature of living groups, whether it's for predation, for prey, for predator detection, and crazy things like echolocation that whales and bats do. Okay, so how do we access these type of data in a fossil? It turns out that it's not just teeth that are hard and well preserved as fossils. The ear region of the skull shows up kind of more frequently than other parts of the skeleton. So here's a deer skull, and back here is where the ear lives. And this part of the skull in mammals is called the petrosal. And that name has a lot of meaning to it. Petrus, petrology, petrified. It means rock. It is a very, very dense, solid bone. And if we take a CT scan of the petrosal here, we can unlock the little delicate cavern of spaces inside where the receptors for hearing would actually live. So we can access these structures by CT scanning a petrosal, okay, the ear region in a fossil. Okay, and I found some petrosals from my locality in the Jurassic of Utah. So this right here is the ear region, the petrosal of an early mammal. For scale, very tiny. So even though this is a really, really, really tiny animal, the ear region can preserve really nicely. So again, through the magic of CT scanning, okay, you can look at how beautiful this bone is preserved. Take away the bone, and that's the space inside. Semicircular canals for balance, the coiled cochlea, and, this is hard to tell, that's the stapes. So that's the smallest bone of your body. It fell inside of there and was rattling around, and it got preserved too, which is really cool. So this is what this inner ear looks like from this early fossil mammal. And if we compare it to both living mammals and most other mammals that were around at the same time during the Jurassic, it's got some cool things. So all living mammals, with the exception of monotremes, not surprisingly, have a highly coiled cochlea. Ours is coiled about 2.5 times. Some of them look like beehive stacks, like a guinea pig and a bat. They have lots and lots and lots of coils. Back in the Mesozoic, most mammals were lucky to have a curl in their cochlea. So this kind of candy cane hook is typical of what we see in the Jurassic. But what we have here is the oldest evidence of a full coil in the cochlea. So lengthening that receptor field, fitting more keys on the keyboard, and higher discrimination of different frequencies. So these kind of data are accessible by looking at fossils. And we can see this story unfolding during the Age of Dinosaurs. So if I go back to this really cool little beautiful skull here, okay, we can CT scan it, and we can look at its ear, which I'll show you in just a moment. But if we scan the other partial skull, okay, like that, this is a slice. This works just like medical CT. You can take a slice through a specimen here, and we can fill in the space that's impressed against the underside of the roof of the skull and generate what the brain looked like in this animal. So that's what the brain would have looked like in this fruitifossor here. So some of the details lost. It's never a perfect copy, but we can get a sense for proportions, which can tell us a lot about the biology of these animals. So for example, this is the snout end of the animal up here. These two blobs that stick off of the front of the brain are the olfactory bulbs. So that's the site where the olfactory nerves that are picking up scent in the nasal cavity, their first stop on their way back to the brain. And the size of those bulbs relative to the rest of the brain is a pretty good predictor of olfactory ability, how much emphasis an animal places on smell and getting around its daily life. So if we compare it to an armadillo, okay, the proportions are pretty similar. And this is not an irrelevant or just so sort of story, because this animal also has a forelimb that's highly specialized for digging. So an animal that spends a lot of its time, fishing around in the ground for worms or grubs or whatever, it's not surprising that they'd have a relatively sophisticated sense of smell. So we can paint a pretty good picture of this animal as having a lifestyle not too unlike an armadillo or something like that, even though it's ancient and not related at all to armadillos. So we have this type of ecology being exploited way back during the Age of the Dinosaurs. If we also compare this to other animals alive today that might have had a similar lifestyle, this adorable little creature here is the African golden mole. It'll fit in your palm. They're teeny little guys. Barely have eyes. Their eyes are often covered by skin. They spend almost their entire life underground. Their skull does closely resemble some of the features that we have in this animal. It would have likely used its snout to do a lot of digging in addition to its forelimbs. But you'd think that an animal that spends its life underground would also need to hear pretty well. And they do, but the inner ear from a golden mole is not really that different from the inner ear in you. And golden moles likely hear way better than we do, but their life is probably happening at low frequencies. Now, if we extract what the inner ear looked like in our fruitifossor, it looks quite a bit different. There are some aspects of the vestibule. This is the part of the skull that is responsible for the senses of balance and the movement of the head in space. That's a different story that I'm still trying to figure out, because that looks very different than what we see in these other animals. But the portion of the inner ear that's devoted to hearing is very unsophisticated in this animal. The ear of this animal is very primitive. So it likely has highly specialized olfaction, so it can smell really well. It's able to dig really well. But something about its hearing is not what we would expect for an animal that spends a lot of time underground. And that can be driven by something else about its biology, or maybe it's actually related to a very ancient lineage that didn't quite have the sophisticated hearing that living animals inherited from their common ancestor. Don't quite know yet. Ultimately, during the Mesozoic, during the age of dinosaurs, we have a variety of really interesting ecological niches that are being explored by early mammals. We've got early mammals that are preserved with flaps of skin extending along the sides of their body, likely behaving something like a flying squirrel. We've got early mammals with flattened tail vertebrae and broad impressions of fur that would have given them a body style not too different from an otter or maybe even a beaver. We've got really small animals. We've got animals that would have spent a lot of time in the trees, and we have lots of evidence for animals that spent a fair bit of time underground. And these are all happening with alongside the story of dinosaur evolution that I'm sure lots of other folks in this museum and our exhibits can tell you quite a bit about. So mammals are ultimately doing a lot of really busy stuff that we can only access by finding great fossils of them. Still, mammals were small, almost as a rule, and likely turned out to be lunch for most of the dinosaurs we're familiar with. Here's a skeleton of a small theropod dinosaur, and in its belly are jaws of a couple of little mammals. Its last meal. Not surprising that little raptor dinosaurs were chomping on our early mammal friends. This is probably a pretty common story. And why mammals probably spent a lot of effort trying to become nocturnal and exploiting those niches when animals that were maybe more cold-blooded weren't as active. However, it didn't always work out that way. This is a skeleton of one of the largest mammals ever found in the Mesozoic. And in its belly, dinosaur bones. So occasionally, dinosaurs became the lunch of our early mammal ancestors. Wasn't a common story, but it's satisfying to see it happen like that way occasionally. So ultimately, mammals survived the big extinction event. Not to say dinosaurs didn't too. Anybody that enjoys birds, you also enjoy dinosaurs. But mammals did it in a very different way and became prolific, dominating in many ways terrestrial ecosystems throughout the Cenozoic, ultimately leading to humans at the pinnacle of evolution, right? The story of mammal evolution is really the story of dinosaur evolution in a lot of ways. Mammals and dinosaurs appear in the fossil record at about the same time, which is surprising to many people. It's just the mammal story was less showy. Mammals were small, they're harder to find, but they were doing lots and lots of tremendous things throughout the Mesozoic. And it's really only through collection efforts and advanced techniques like micro-CT scanning that we can unlock a lot of this information about them. With that, I'll say thanks for listening. I've got a graduate student. This is Bridget Connolly out in the deserts of Utah last summer. She's working on the skull of that little burrowing mammal as her dissertation project. So some of this was stuff that she'd been working on, and I'm excited to see what she learns about that animal. But ultimately, fieldwork is where all the fun stuff happens. I'm super jealous of all the rocks you guys have around yourselves here in Drumheller. Kentucky is lovely, but you can't walk out your back door and have a non-zero chance of finding a fossil. I'm happy to take any questions, and thanks so much for listening.